Our last day, I'd like to tell you a few words about the lensless optics. The lenses are difficult to make. They are expensive. They have to be made they used to be made only from the glass. And if you need a really high quality optics, it's still a glass optics. But if you want to make it cheaper, it's made out of plastic. Then the plastic is not so durable as the glass. On the other hand, the glass can be easily broken. And I remember my first glasses were glass, made out of real glass. And a month after I have them, they fall on the floor, and I had to get another one. And but the lenses also have whatever is the material out of which they are made, they have a limitation. And the modern optics is trying to avoid lenses, and that will be a short course of how you can do this. And the first thing is the very concept, how you can replace the lens by an electronic device or whatever. There is a kind of a spin-off of looking at what we have been discussing so far from the viewpoint of the lensless optics, is that we discover that we can apply the same technique and the same way of thinking about the forming images as with the lenses to the other forms of the radiation. For example, we can combine optics with acoustics. And that is extremely important in various applications. One of the applications where one of the biggest achievements of the conventional optics, which is called the hologram, was used where the acoustic waves are interwoven with the optical radiation, electromagnetic radiation, is the search for the submarines, where the acoustic trail left by the submarines on the surface of the ocean or a sea can be picked up with the electromagnetic radiation of a radar flying, of a plane or whatever flying above, and then it is converted, and we can not only register that here in this given area there is a submarine, but also see its shape and it see its physical properties. So the first few minutes will be devoted to the analysis of what is called a filter. A filter is a word to describe the following physical situation. I have a signal, and the signal which I'm sending is, for example, electromagnetic wave, but it can be acoustic wave, and it can be basically anything which is kind of a wave, and it has a certain spectrum. So the signal depends on the frequency with which I'm sending, has a certain frequency. So I will denote the signal with the capital X, and it depends on the frequency. And somewhere else, I have a device which picks up that signal. It is a receiver, and in this language, it's called output. So I have an input radiation and output, and that output is denoted by the capital Y. It also depends on the frequency. And the filter is basically everything which converts the signal into the input into the output. So it's a black box which I put between the incoming radiation and outgoing radiation. One of those black boxes, which usually isn't really black, we were discussing last week or so was a lens. The lens is a box which you put between the radiation which is coming and then leaving. And as we know, it has a different refraction index, and that depends on the wavelengths. So it serves as a filter. This also is a filter. And the filter might react differently to the different frequencies. So I will call a filter with the capital letter F. And as the filter input and output live, so to say, in the frequency space, then we know that by the Fourier transform, we can look it up in the other part of our world, which is the time processes. So if I have the frequency spectrum, then I can easily see what was this process in real time. And if I will be discussing a time domain description of a signal, it will be little x, which depends on time, and the output will be the little y depending on time, and the filter will be the little f, which is also depending on time. So the linear filter means that it acts on the input in a linear way. So the output signal, y over omega, is simply a product of these two functions. So that's very easy in the language of a frequency, but then the mathematics tell us that in the time space, time version, that is not a product. It's the integral relation, which is called the convolution. So that is what really is happening with the signal. It's time, this time process is modified by the filter, and this modification depends on the process of time. In physics, we learn, in the previous lectures, we were discussing, for example, a dielectric property of a medium. But the dielectric property of a medium that can also act as a quotation filter, because it might depend on the frequency, and then this phenomenon is called dispersion. So in various areas, we will be using the same formula, but using different words to describe what we are talking about. So this is how the filter works. And let's now try to see what we can learn from it. First of all, we have a mathematical property of integrals, which is called Cauchy-Schwarz inequality, which says that if I have the y equal to convolution of x and phi, then if I measure the strength of the output by its square, as it is written here, then it is a square of the integral of x and phi, and then the property of integral tells me that cannot be larger than the product of the strength of the signal multiplied by the strength of the filter, so to say. This is a purely mathematical property which is valid independently of what I assume of the x and y and f. So let me apply that Cauchy-Schwarz inequality to our definition of a filter, and then it is very trivial. Then the y square is, should be less than equal. There's a little mistake. It's in there even. So I don't see that so well on this middle screen. So then the integral of the input times the integral of the filter. So this is a certain inequality, and that inequality can be saturated, achieve its largest possible value, if the amplitude, there is a square missing. There is still a mistake there. There's a square missing. I'm sorry. So the saturation of that inequality is achieved when the filter is basically the input, complex conjugate, and with reverse time. So if I manage to manufacture a filter which has this property, this is what is called a matched filter. And that is used to detect known signals. For example, I'm building up a radar which is only supposed to react to well-known Tomahawk missile which is coming to me, which wants to ignore everything else. Then I know what is the shape of that device, possibly, and I can manufacture the filter, manufacture the function f, and make a filter which has this time dependence, and then what my output will tell me is only when there is the strongest signal in my output device will be when the Tomahawk is coming. Whether that will help me, that's another issue. But that is, so this is what is called a matched filter. All right, so we know something, and let's now look how we can describe our known lens operation in terms of these notions which I just have introduced. So I have a picture which is a lens, which is my thick line in the middle of a screen, and it has a certain this length, which is d, and that is what is called the language of the lens's aperture. And somewhere to the left of my lens, that was our convention which we used before, I have a source of radiation which emits electromagnetic wave, and the source is at a position, this is a two-dimensional picture, so the x is the vertical axis, and the z is the axis from the, so to say, source to the receiver. So the radiation is emitted from my source, and it hits the lens at the point which I had chosen arbitrarily to be at z equals 0. I mean, I avoid another z in my calculation, but that is just completely irrelevant. So the radiation hits the lens at various points in the aperture, right? All right, good. What happens to the radiation when it comes to the lens? It is an electromagnetic wave, so it propagates, and its phase will be changed and also because the phase depends on the distance, but also the amplitude. But the spread of the amplitude is always order of magnitudes, is the lowest order, is the highest order correction, as we used to say in mathematics. Therefore, I will be concentrating in this sketchy calculation only on the property of the phase of electromagnetic radiation. And I can calculate the phase of electromagnetic radiation hitting the lens by multiplying it by a certain function, which will depend on what? On what it can depend? It can only depend on the point of the emitter, point where it hits the lens, and the distance z. So it's a function of these three variables. So what is now happening with our signal? It hits the lens and goes out of the lens. And it is modified in the lens because something those photons do with the atomic levels of the probably compounds, chemical compounds out of which the lens has been made, So it is modified. The signal is modified, and this modification depends on the point where the light has hit the lens. So I will call that modification as a G with the index X. And then it goes on, and eventually it comes to my receiver. And the process, so the combined function, which does the change of the radiation from the source, from the emitter, to my receiver, wherever it is, I will denote as a function d, because it's the distance, of which depends on what? It depends on the point x and on the point z, because I don't know where I will be receiving it, okay? So that is our geometrical structure. And clearly, the lens is hidden in this function g, its property. And as in all our calculations for mathematical simplicity, we will be using this paraxial approximation. That is, I will be assuming that my lines tangent to the k vector of electromagnetic wave are close to the axis, optical axis of this device. In that picture, that is easy to see as an inequality paraxial axis over which I have to, the distance over which I have to calculate the function f is that x minus x prime is small as compared to the distance, because I am looking on of the trajectories which are close to the optical line. Okay, so let's now repeat this picture and let's do the calculation. So what is the function f? It's the phase shift over the propagation distance and over the distance from the emitter to the point on the lens. So this is e to the power ikr, where k is a wave vector of the radiation. That is one of, well, it's 2 pi over the wavelength of the light we use in the experiment. But the distance can be easily calculated by a trigonometry, so that is the function which is written in the expression, and I can modify that in the form, and then I can apply my paraxial approximation. Because x minus x prime is small as compared to z, then I can take e to the ikz out of the exponent and expand the rest to the first order, and therefore I have my function f in an explicit form, and this is just the phase shift when the wave goes along the optical axis of the device, e to the power ikz, times this addition factor, which, as you see, depends quadratically on a distance along the aperture between the emitter and the point of the lens where the radiation hit it. So now I calculate my function d, and the function d is the integral over all aperture of the property of a lens, which I denoted as a g, times that function f. Since I already know what is the function f, okay, then I now make an assumption that g is a matched filter for a given wavelength. So that's trivial. If in order to make this to be a matched filter, then it has to be the complex conjugate of a function f with the x changed. Now my signal depends on a distance, not on time, but that's a minor mathematical problem. So since I know already the approximate for a paraxial approximation form of a function f, then I can immediately calculate the property of a matched filter, and that is given by the simple exponential formula. So at the axis, so at the optical axis, the matched filter depends exponentially, but with the distance square from the center of the lens. If I go over the aperture, it's the largest on the middle, and it decays when you go to the both ends of the lens. So now I can calculate the function g. This is easy exercise in the integration, and I get that the function d is first of all proportional to the aperture. Then there is this factor which depends on the x square, and then comes the complicated function which is a sine divided by the other side. Now k is the inverse of the wavelength, so I can write the function d in a very simple form. And this function sine of x divided by x in mathematics is called the sinc function. And this function has a very peculiar property. But in any way, the d is now the description of the system which tells me what will the output device register if I have an emitter at the point x and z, which sends the radiation to me. And as you see, it is almost everything is gone there, with the only difference is d, the aperture of the lens, and of course the wavelength. So if I want to get rid of my lens, right, I can remove the lens and put up some electronic device, a filter, which will just have this mathematical property, which is, as you see on the slide. And then I can do whatever I have done with the lens, I can do without it. That is how this function sinc looks like. And as you see, it has many oscillations, but it has the central peak and many side bands. But when the d, the aperture of the lens, those artificial lens, right, goes to infinity, that function goes to a delta function. And for any, so how do I now use this property of that function to look up at the resolution of my device, my filter? Okay? That is how the receiver sees the source, so to say. It sees the main peak and sees many sidebands. But that is, of course, for radiation coming from one point. So the resolution tells is, how can I distinguish features of the source if they are divided on the source by a certain distance? Okay? So I have to look up how can I define it by looking at this function. Okay, that's very easy, and that was done by Mr. Rayleigh back in the 19th century. He said that that's very trivial. I have the one point, and the radiation coming has a maximum and has a first minimum. You can see the first minimum, right? And the other point sends also radiation, so it is represented on my output also as this kind of a sinc function. So if the maximum of the sinc function corresponding to another point on my emitter is located in a minimum, first minimum of the first point, that is the definition of a resolution of my device. And that is the Rayleigh definition. And equipped with the simple formula and with which we have seen, and with this definition, it is easy to solve essentially all the battering problems. For example, you can easily calculate what will be the required dimension of a lens, if that was a lens, for trying to build up a camera on a satellite flying 200 kilometers from the Earth in order to see a registration plate on my car, distinguish the letters on my registration plate. That is not that the size is considerable, so there is a lot of additional electronics which is necessary in order to make a good quality spy satellite traveling. One of the tricks which is used is that since the resolution depends on the aperture, it will be nice to do the devices with a huge aperture. But the satellites cannot be too large, so how do we can manufacture a huge aperture on a satellite? And that is a clever invention which is called artificial aperture, which means that the satellite, and that is how the radar is scanning the Earth's surface, for example. The satellite is making pictures from different points on the orbits, and then the whole orbit is the aperture for a given scene. So if they send to us the picture taken from many points, I mean, on the orbit, then we get a huge aperture, so we can get a very good resolution. So if I have a satellite which goes extremely fast on the orbit, and the car which is moving very slow on the Earth, then the satellite can make a tremendous number of pictures and get me the good resolution without necessarily having a giant mirror or lens on it. All right. So this is also how the phased radar work. The phased radars are the devices which have been for years and years secret devices. Then that is the one which is in Google. So I'm allowed to show you this. And this is one possible geometry where we have lots of little detectors which measure the same object, and out of that they can easily recognize the shape. The phased radars can also look, and that is an interesting geometry problem, they can also look over the horizon. And one of the largest phased array radars built up to look on the other, beyond the horizon, was built in the former Soviet Union next to the nuclear power plant in Chernobyl. And when the Chernobyl exploded, this giant construction turned out to be a region which was evacuated. So it's sitting there, rusting and not being used. And since that, the technology has improved, and this first phased array were huge grids of receivers, and now they are towers like this, and that is one of those applications. The other application of it, which will be essentially our last topic, is a coherent imaging. If I am sending the electromagnetic wave with the well-defined frequency or wavelength, that is what I call the coherent radiation. And that coherent radiation has the property that I can do a decent interference on an arbitrary distance. Sure enough, there is no way to manufacture a coherent radiation so good that it will be really very completely coherent. Even the best laser detectors are not that well coherent. They are superbly coherent, but there's also limitation. And that limitation is given by a certain uncertainty relation Namely, if I send the radiation, if I have a little error with the frequency, then there is the frequency time uncertainty relation, essentially that one which we know from quantum mechanics, and that means that if I have a certain spread in a frequency, then there is a spread in a time, but then if I multiply that spread of time by the velocity of light, then I get a spread of length, and that is the coherence length, which is defined for the devices, and we will see in a moment how to use it. And the coherent imaging is incredibly powerful device used in thousands of experiments in physics, but it is also one of the most clever application of the coherent imaging is in medicine. And one of the devices which I'm advertising here is a coherent imaging, is a coherent, how do they call it? It's SOCT, spectral tomography, and that is used to check our eyes. And the first commercial computerized this coherent tomograph, which is capable optical coherent tomograph to check the inside of our eyes, was built up in Toruń in Poland, and that is a side product of the tremendous progress in optical experimental physics done by our colleagues from the Copernicus University in Toruń, and that I believe is essentially the only high-tech device which has been commercialized in Poland. It is now being produced en masse there. The company, as far as I know, is now owned by Panasonic, but maybe by other company already. They are selling and buying, so I am not coming. But this is a great device, so we will be. And that is the first thing which I would like to discuss is a hologram. And the hologram is that picture. We have a coherent radiation which comes, and it's being splitted. There's a device which is called the beam splitter. So the part of the beam goes through, and the part of the beam which has the same properties, so it's the same electromagnetic radiation with the same wavelengths, it goes in the other direction, and it hits the object which is the blob on my picture. And of course it's reflected from that blob, and it goes to the receiver, which is on the right on the picture, and there is and then on that device it interferes with the beam which has been sent through. So we get on a plate, photographic plate that was originally played, we got the picture, which is the interference picture between the beam which went through and beam which has scattered. The beam which has scattered from object will be denoted as a phi. The phase of it will be denoted by phi, and the beam which goes through and its amplitude and phase will be denoted by phi with the letter r, and then it will be the transmitted beam which I will denote as a phi over t. So the beam which goes through is again a plane wave, so it's e to the power minus ikr, and this is again a two-dimensional calculation. So what happens with the beam which scatters from object? Well, it will have a certain amplitude, A, and it will have a certain phase, right? And this amplitude and phase, they carry the information about the property of the object. I have assumed that my reference beam, VR, they call it reference beam, have an amplitude equal 1, but that is only because I want to keep the calculations as trivial as possible. I mean, sure enough, it may have another amplitude, but that will be just another letter in my calculation. All right. So that is basically how that looks in experiment. And that picture which I got on the plate is called the hologram. And now what I do in order to see something on it, I'm taking my plate, go somewhere else, and because I know what's the radiation used as the reference beam, I'm sending on my plane again the beam which has the same property. And that beam now scatters from that interference pattern, and it generates a variety of objects, so to say. There is a imaginary image which is formed somewhere. There is a real image, and I see something on my thing. So what I see, okay, that is the picture. I can easily calculate what is the interference pattern I, okay? This is the, it is a square of the, I had to add phi O to phi R and take a square of it. And then it's a very simple algebra of complex number, and that is what I got, what I will get. So this is a picture. There's an incoming reference beam. There is my plate with the encoded information I, and then it is a transmitted beam. So that is a very simple calculation to show that the beam which comes out is essentially the same which has been scattered from the object. There are some additional little terms which I ignore because they can only be taken care of by having a proper geometry. And these additional terms are easily visible if you buy a cheap hologram. For example, on my, I believe still on the tram tickets and in old times where the software was sold in boxes, the Microsoft were attaching a little hologram, and that wasn't a really good hologram because it was not, you didn't have exactly the reference beam, so you will see the picture which was a little bit blurred, and you have to turn this object, and the easy way to see it very carefully was to take a slit, take a piece of paper, make a slit in it, and look through via the slit on the hologram. So that is how the hologram basically works, and that's a history of a hologram. The hologram had been, in some sense, invented by this curious individual, Mr. Mieczysław Wolfke. Mieczysław Wolfke was a Polish physicist who twice in his life made incredible discovery, and somehow he missed it. The first was when, right after the First War, he went to Holland, to Leiden, and was working with Kamerlingh Onnes, the man who discovered superconductivity. And the way how Onnes discovered superconductivity was that he was able to achieve a very low temperatures at the time. And the only way to get the very low temperatures at that time, essentially 100 years ago, was using to liquefy helium. And Onnes was able to liquefy the helium, and he liquefied the helium and had the dewars full of the liquid helium. And both of them have discovered with Wolfke, I mean, actually not even Onnes, but the Onnes assistant and later on replacement, Kazum, had with Wolfke, they discovered, and they wrote a paper on it, that if you cool a helium-4, at that time it was the only isotope known, below a temperature of roughly 2.7 kelvins, then something happens to that liquid because a dewar becomes quiet. If the helium was liquefied and kept it in a dewar, it was vaporizing very rapidly. And if you, well, you know, if the liquid is vaporizing, essentially it boils, right? So it makes a noise because these bubbles burst and so forth. And when they chilled the, so to say, the helium below 2.7 kelvins, then they realize that something is happening because it becomes very quiet. And they never tried to do any experiments with that helium. And that was, of course, a superfluid helium. So they discovered the superfluid helium, but they didn't do any experiments on it. And and they even invented the name for it, which is still used by the helium physicists. They call it helium-2, the Greek, the Latin 2. Helium-1 was simply liquefied helium, and helium-2 was that strangely behaving helium. They didn't make any experiments on it, and it took years before people in the basically Rutherford laboratory in England, they find out that it might be very interesting to look at it, and independently, Peter Kapitsa and Atkins, I forgot his name, first name, they make the experiments and they find out all these incredible properties of the helium, and eventually Kapitsa got the Nobel Prize for it. So that was one of the experiments Wolfgang has done, and he missed the biggest discovery. He then returned to Poland, became a professor at Warsaw Technical University, and becomes very busy with optics. And in the 20s, he brought a paper in which he basically described what I was telling you now. And he described essentially the full experiment, and somehow he never did it. Nobody did that experiment for years and years and years and years. Wolfgang was a very interesting gentleman. He was he was the first known Polish scientist who openly worked for army. He had an institute at Warsaw Technical University, which was called the Military Physics Laboratory. And he was also, in the 30s, what was very fashionable were the stratospheric balloons. There was a fellow named Pickard in Switzerland who made the first balloon with which he meant something like 30 kilometers up there. That was the highest how people went, and they were able to see the curvature of the globe in a very beautiful way. So the Wolfgang built up such a balloon in Warsaw, and they were supposed to fly that balloon in September of 39. In the 26th or something of August of 39, that balloon went east of Poland. They were somehow oblivious to the war coming, and they were supposed to start from the river Stryj, which is now Ukraine, and they went there, and the future of the skin of the balloon and the whole equipment is at least to me unknown. And Wolfgang went into the hiding. And after the war, he was a professor at the Technical University in Gdansk, where Poland regained the access to the sea and the Gdansk. And there was a German Polytechnical Institute, which becomes a Polish Technical University. Wolfgang was there a professor of physics, and there was still possibility of traveling. And in 1947, he went to Switzerland, to ETH, because in the 30s, he was also a guest professor at ETH in Zurich. He went to Zurich, and in a very unknown situation, he died on the street of Zurich, apparently of a heart attack. So Wolfgang was, in fact, a discoverer of hologram, and when Denis Gabor, a Hungarian British physicist, discovered the hologram again in the 40s and after the war, and actually made the first holograms, for what he got the Nobel Prize in 71. Then in his Nobel Prize lecture, he mentioned that this is what he did, was initiated actually by Mieczysław Wolfke. But of course, the rules are that you cannot give a Nobel Prize to the person who is deceased. So that is, but the Wolfke was remarkable, completely remarkable. He made many. The Warsaw Technical University was a strange institution where strange characters were teaching physics. There was another assistant of a very famous Dutch physicist, Bruno Wienaver, who was the assistant of a Zeeman, from Zeeman. And Bruno Wienaver came to Poland after the First War and became also professor at Warsaw Technical University, but very quickly he figured out that Poland is not treating professors sufficiently well, so he quit and becomes a writer. And he wrote an enormous amount of books and plays about physics. I mean, you have to read it in Polish. And he was also the first translator in Polish language of the poetry of the Bertolt Brecht. Okay. All right, so the final thing is how the optical coherence tomography, the eye tomograph, works. You have a source, and the source is of a radiation which is not coherent. There is a spread of the frequency. So it goes, and again goes via the beam splitter. It's scattered, it goes to a mirror, which is movable, so I can scan the mirror a little bit. And then it goes to the sample, scatter of the sample, comes back to beam splitter, and is scattered to the detector, where it is picked up together with the signal which scatters from the mirror. And now, if the both signal were coherent, the scattered from the mirror and from the object, then I will have a very strong, my detector will register a very strong signal. But if they tune, then there is a phase shift between the signals which I am receiving, and that phase shift I can modify by slightly moving the mirror. By moving the mirror, that is the same as moving the point of a scattering of a beam from the object. So I'm moving a mirror slightly, and that is equivalent to picking up in my interference picture in a detector, to pick up a signal scattered from object at a different depth. So with this, I can shine a beam of light, slightly incoherent beam, into my eye, and by changing somewhere the mirror, I mean, this is easy to say, very complicated to make. Took years to construct it. Then I can probe the eye at a different depth. So I can scan the inside of my eye using a very low intensity electromagnetic radiation. So it doesn't really make any damage or any discomfort in the eye, and it can provide a very detailed picture of how our eyeball looks from inside. And that is extremely valuable tool for ophthalmologists to check what is happening in my eye. So that is really existing device manufactured in Turin. And slightly differently, because of the complication with the three-dimensional picture, is a real tomography. I'm not going to talk about the real tomography because time is over. Maybe next semester we will be talking more about various devices which are built up on the base of mathematics. But what is important is that the tomography, real tomography, is basically three-dimensional by constructing many two-dimensional pictures. So what is not on this picture is that you have to do the same operation like here, but on a different plane with respect to our drawing, okay? So I have many of those pictures, right? I'm slicing the eye or a person, if you're doing a computer tomography of your body, I'm slicing that and then I have lots of those slices, and if I want to get the real three-dimensional picture, then I have somehow to combine those slices in a proper mathematical way. And that is, this is based on some integral transformation, which is called the radon transformation, slightly similar to the Fourier transformation, but a bit different. And the result, if I want to construct the image, I have to solve enormous amount of linear equations. And the solving of the linear equations, a huge amount, is only possible on the computer. And, but lots of the equations was also important before the computers were invented. And at the time, mathematicians were doing some work on how to quickly, and maybe not exactly, but in a good approximation, solve a very huge set of linear equations. And one of the tricks was invented by one of the algorithms to solve the large sets of linear equations in an approximate way, was invented in Lwów, in Poland, pre-war war, and by one of the members of this Lwów School of Mathematics, Stefan Kaczmarz, who was an incredible character. And he was killed on the first day of the Second War because he was an officer in the army. And the Kaczmarz algorithm was there, but there were no computers to really use it. And when McCormick and Hansfield built up a first computer tomographs, for which they got a Nobel Prize, then in the McCormick lecture, McCormick is a mathematician, there was in the 70s, he mentioned that the algorithm he used was the Stefan Kaczmarz algorithm. And it's still being used. I mean, in any program of the computer tomograph somewhere, as they said, it's shown in is the algorithm of Kaczmarz. The computer tomograph is an extremely cute mathematical construction to read the picture, but it is still a picture where there is a radiation coming in and leaving, scattered to observe. Another imaging technique where there is no radiation coming in is the nuclear magnetic resonance imaging, which is illegal to call nuclear magnetic resonance because nothing good can be nuclear, so it's called magnetic resonance technique. And nowadays we have the only medical technique which uses antimatter. Actually, it's the only human activity which employs, when we are speaking, there are probably hundreds of people, even in Poland, who are now being treated with the antimatter. And that is what is called the positron emission tomography. And that is, of course, a completely reverted procedure where the humans are emitted of radiation. No radiation is coming to us, no field is applied to us. We are radiating electromagnetic radiation coming out from annihilation of the positrons with electrons in our body. So we inhale the radioactive element, which emits in a decay positrons, and the positrons annihilate with electrons in our body, and they give a radiation, and we measure that radiation. And there is, of course, complicated imaging, how that radiation is picked up. And that is a completely computer graphics. In all what we were discussing, there was a real object which is illuminated, and the only problem was decipher the information from the pictures we get. But there was a real object, okay? It was really something on which something was scattered. In the nuclear magnetic resonance and in positron tomography, there is no real object in a sense, unless we know from experiment how the positrons are annihilating with the electrons in a given cell, or unless we know how the hydrogen atoms depolarize in a changed magnetic field in a given cell, and what is the difference when the cell is sick and when the cell is healthy, then we don't know anything. Those pictures which you get from on a disk when you go to the doctor and they do the magnetic resonance or something, they are complete computer graphics. They are not real pictures. They have been pictures constructed by computer program from measuring a very simple few numbers only, 3 numbers in magnetic resonance, and that is, of course, why this is extremely difficult to have it. And as you might know, there is something which is called a functional magnetic resonance, fMRI, which permits to measure time-dependent processes, and they are extremely sophisticated software devices. We have two fMRIs in laboratory of Professor Skarżyński in Kajetany, and I believe there is another one at Medical University, but I'm not so sure. And it turns out that 2 years ago, that the company which manufactured this software made a mistake, and that many of the experiments done by fMRI have to be redone because they were in some sense faked. I mean, they were not. Okay, so we had this. This is again the syllabus, what we have been talking about this semester. There are some references if you want to see the books I was using and the papers, most of them I believe. There's a book by Gershenfeld which is highly recommended. I use it a lot because it's a very good book on the physical basis of a contemporary information theory. And there is an old book from, at least I have the copy of it from '79, which is the Introduction to Optics. It was even translated into Polish, which already in '79 has many interesting information which are now, of course, in everyday use. So thank you for being with us for this semester. And enjoy.